Okay, so we understand why we should care about them. Let's jump into arrays and linked lists. Now, to understand arrays and linked lists well, I think we need to understand what's going on underneath, what's going on in our computer's memory. So let's start with arrays on this side, and then we can compare them. So an array, we talked about how arrays are, well, Sophia briefly mentioned it, that arrays in memory are continuous. So imagine each box is a drawer and it's going to store one item, right? So for an array in memory, it's going to be continuous. Does that make sense? Yeah. So
Yeah,
if I'm
like
on,
it grabs like a address and runs through in a given like block of memory to wherever you need it to end, more or less. Is that what you're saying?
absolutely, yes. So if I said, hey, I need to store two items, I'm going to get two drawers right next to each other, if that makes sense. Now, unlike this chest of drawers, a computer is also going to give each drawer, each box, a memory address. So for the sake of simplicity, let's say this memory address is 0 and this one is 1. That, of course, isn't going to happen with a real like chest of drawers, but that's what an array is going to do. A linked list works a little differently. Please clear. A linked list is going to tell us, hey, if I tell it I want one item, it doesn't care about being continuous. It's going to give me a box wherever it can find one, right? So if I say, hey, I want to store one item, cool, here's my one item stored. I want to store my second item, here's another one. I want to store another one, here's another one. Here's another one. It's just going to keep on going. Now, the difference is, does anyone know how it knows this is my first, this is my second, this is my third, this is my fourth? Does anyone know? Any ideas? You don't have to know, of course.
You have a pointer to the first one and it has a pointer to the second, and so forth.
Yeah, so it has a reference. So like if we draw a magnifying glass and we go in deep on this first one, what you'll really see is something more like this. So here's the item I'm storing. Let's say I stored an apple in there. It's in this second area thing, it's also going to have a reference to the memory address of this second box. So, what happened to my, okay. It's also going to say, hey, this one is located at F null, blah, 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 right? And so forth and so on. So it's going to store its item and it's going to also contain a memory address for this one and also a reference to this one. Now, those may not seem like huge differences, but it does result in pretty big differences in terms of how easy it is to insert things and how easy it is to add new things and take away new things. So an array, the easiest way to think of array, at least the way I think of it, is an array is like a really cliquish group of friends, right? And let's say this cliquish group of friends wants to go to the movie theater. They all want to sit together. They're a clique, they're the cool kids. They're gonna want to sit together. Now, let's say one of the cool kids arrives late. Now, the cool kids, they're gonna want to sit together. They're not gonna want to be separated. And let's say like there's another thing right there. For the cool kids, it's not gonna be okay for one of them to be here, right? So what they're gonna have to do, if I wanted to add this new friend to the existing array, is they're gonna all have to move, right? They're gonna all have to get up and move. Now for a computer, that gets very annoying very, very quickly. If ever I want to add something, I have to go ahead and find a whole new location that can fit absolutely everything that I'm looking for. Does that make sense? Yeah. Do we
Yes.
have any questions about that?
Is this the idea of like expanding an array is expensive? And if so, what is it expensive in? Is it like processor expensive, storage expensive? Like, why should we avoid it if we're trying to optimize for a given, concern?
Yeah. It's expensive in terms of it can be expensive in terms of time, and it can also be expensive in terms of space. So one solution, I'll explain that in a second. This will explain it a little better. So one solution that people sometimes do is, so if I'm the cool kids and I have 5 friends coming, why does it, okay. I have 5 friends coming, but right now, oh, I'm sorry, I said that wrong. I'm the cool kids. I have an unknown number of friends coming, right? So what I might do is like, I'm just gonna hold all these boxes. Yes, for now, there are only 5 people here. I'm gonna go ahead and hold them. So just in case a new friend shows up, I have space and we don't have to relocate. Like imagine in a movie theater, you having to get up and like your entire group moves to another area of the movie theater. That gets annoying. You don't want that. So let's say only 2 new friends show up. We have just wasted all this space. So I'm not using it and nobody else can use it too. And depending on how small the thing you're working on is, how little memory it has, this can be a big problem. Nowadays, it's not that big of a problem because we have a bunch of space, we have a bunch of memory, but this can be a big problem if you're working on something small. I had a professor working on like microprocessors, and this was a huge problem. We were building robots, so this was a huge problem, wasting space. A linked list, of course, avoids this problem by just taking space wherever it is, right? Does that make sense? Does that answer the question? Yeah. One disadvantage of an array, though, is, actually, let's not talk about that yet. Why don't we talk about, let's run through a few scenarios. Let's say.
Can I ask a quick question real quick?
Absolutely.
So for functional reference, the list that you create in Python is going to be a linked list. And then in order to create an array, would that be like you'd have to do like a pandas array for that?
I've never worked with a pandas array.
Or a NumPy array, I think.
Yeah, you could definitely do that, or you could implement your own for like a pure, normal, regular array. You
Like
could implement your own.
like create a class that treats data like an array.
Yes.
Okay.
Yeah. We won't be talking about how to like make a class that treats data like an array, but we will be talking about how to make data that treats class as a linked list. And once you understand how an array works, honestly, making the class isn't that difficult.
Yeah, just to add on to that, Python's list does a lot for you. It has like basically all of the functionalities of a stack, a queue, and a linked list. This isn't the case for other programming languages. So for example, in Java, we have arrays that are fixed sizes and array lists that are dynamic, which Python automatically does for you. But yeah, as Praise was saying, and I think Jack touched on a little bit, I think the way that Java expands array lists, which are dynamic, is that once you try to insert another element that exceeds the size of the array, it'll double, and that's what costs more time. But like on average, the amortized runtime would be O of 1 for insert. But when you do need to copy the contents of an array to make more room for a bigger array, that's where like memory allocation and like freeing the previously allocated space takes up time and space.
Yeah. Okay, so real quick, we're gonna run through different operations and we're just gonna think through it together. Like this is new information. No one's expecting anyone to know anything. So a guess is wonderful too. So let's say I want to insert into an array in a linked list. Which one do you think might be better for inserting, like right smack dab in the middle? Would I want to go for an array or a linked list?
I would assume an array.
An array? Why do you say so?
Because you're just inserting in the middle. Because with the link list, like it's not like you're placing it elsewhere. Now, if you was placing it like let's say, for example, a different server or something like that, I can understand that. But let's say if it's a similar location, if not the same location, which is putting in an array.
The linked list, you just pop it in anywhere and then adjust the pointers.
Yeah, so we wouldn't want to put it in, we wouldn't want to use an array to insert in the middle, like a pure array, because remember, arrays want to hang out together, right? So an array would have to, so let's say this is my array. Actually, let's just go back to the other page. Boom, boom. Please go back. Okay, so an array would have to, so let's say this is my array here, and I want to insert an object right here. In order to do that, they would all have to get up and move. So these, it would have to recopy itself and then place my new item.
Oh, okay, gotcha.
Does that make sense?
Yeah.
It would be able to do it if, let's say, I had saved a bunch of space and it wanted to just add it to the end. That could be done, but to add it right smack dab in the middle, it would need to recopy itself. Why would a linked list, Don already mentioned this, but why would a linked list work better? Any ideas for why a linked list would work better? Remembering that a linked list works by storing the item and then a reference to the item, to the next item.
Is the idea that in a linked list, I don't know what the terminology, I guess each item in a linked list is only worried about like one other item position. And so if you wanted to insert into a linked list, you're only having to change like 2 items, their reference points. Whereas
Yeah.
in an array, since every single item has to know where every single other item is, it's a lot more difficult.
Absolutely, yes. So you're right, unless it's like a doubly linked list, which just means it has a reference to the one before it and the one after it. A normal linked list, a singly linked list, only has to worry about the one after it. So you're right, all I would need to do is change the references when I add my new one in the middle. Any
Gotcha.
questions about that? Okay, let's head back to our page. Okay, so yeah, we would want to use a linked list to insert. Can anyone tell me what the big O of that is? We haven't had much practice with that. What would the big O of inserting it into a linked list be? It can do it almost instantly. It's a bad word, but
I Googled it, but apparently it's 01.
yeah, constant. It can do it just like that. Versus an array where it would have to iterate through the whole entire thing and copy it out, making it O of n. So if I have n items, it would need to do it n times. It needs to copy n things, right? So we definitely want to use a linked list to insert. What if I want to access an item in the middle? What if I want to say, hey, bring me the item at the middle of this? Would I want to use an array or a linked list for that?
An array,
An array, why?
because you can access it by index, and that is effectively also free.
Absolutely, yes. I would want to use an array because remember, an array, since it's continuous and it has those memory addresses, I know if I'm number 1 and you want the item in number 5, all I have to do is move 4 spaces down and I found it. Unlike a linked list that has to travel through each one until it finds the item you're looking for. So can anyone tell me what the big O of accessing an array would be? Accessing an item in the middle of an array would be?
O of n.
Not for an array. Remember, it already knows where it is.
O of 1.
O of 1. Does that make sense why it would be O of 1 and not O of n? Because it can instantly get to, let's say, the 5th item because it knows where the 5th item is because it's continuously stored. Does that make sense?
Yeah, kind of.
So you don't have to like iterate through the array to find the 5th object. You can just know where the first one is stored in memory and then add 4 to that. And that's where the 4th element or the 5th element is stored.
So a linked list is you have to iterate through all of them instead of just pointing at the right one that you want to go to.
Yeah, remember a linked list is like this. So this is my first item. I don't know how to get to my second item until I look at the information here. Then I can go to my second item, but I don't know how to get to my third item until I look to the information here. So let's say I'm looking for the fifth item. I have to go through all of these until I find that fifth item, right?
Oh, okay. So it's kind of like a maze then, where you just got to keep traveling until you find whatever.
Yes, absolutely. You
Now,
just
why,
have to.
why is it that you're able to insert without, like, you don't have to go through each one to change the memory address that it points to? I mean, like, why is that not, why doesn't that take up more space or more time?
Yeah. Well, look at the operation by itself. So don't think like, hey, I have to, if I want to insert at the sixth item, I have to travel to number 6. We're just talking about how long would it take me to insert, not necessarily like would I need to transverse and
Well,
then.
yeah, but with the two sets of information, there's one side of it that's the actual information, there's the other side of the pointer, but anything coming at that point or after that point should change the access information for the object, no?
So you're saying if I change one pointer, I should need to change all the others too?
Just for the ones after it, wouldn't you? Or no?
Not necessarily. I hope I'm understanding.
Okay, so I guess the action would be more along the lines of, I think I'm just having some trouble processing.
Will I have like a document that I used to study this stuff, and I can share that. Hopefully that, I think that will clear up the question you have a little better, because I'm not sure I'm understanding you the question. I don't want to waste your time. Or
I
Rena,
think this is about the linked list having the memory address to the next object on the list. So when you add something in, it just points to the next object, and then that object points to the former second object, but their positions in memory haven't changed.
Yeah.
If you know the object you want it to follow, all you have to do is change the pointer in the existing one to point to the new guy, and change the one in the new guy to point to the one that the existing one used to point to. But I think one of the things that Andrew was suggesting is that it can be very expensive to figure out where it is you want to insert it in the linked list.
That is true. Yeah. So a linked list, we talked about how it has to travel through each one. So that is true. Figuring that out might take time. Transversing through it will take O of n time, but the actual insertion itself will only take O of 1 time. Okay, so this is the last one, I believe. Oh, actually, I think we're good here. We already talked about what it would be like to insert at the end. So we are all good here. All righty. Okay. Now let's implement a linked list. But before we move on to doing that, do we have any questions about linked lists?
I have a question. Would deletion be the same runtime as insertion, assuming we're deleting at the end?
To delete at the end of an array or?
Or linked list.
Yeah, it won't cost you. What do you mean?
Let's specifically, like, let's say if we wanted to delete a node, but the node happens to be the tail end, so it'll probably be O of 1, whereas if it was like somewhere in between, it'll probably take like O of n times, because you have to iterate through the list to find that specific node.
You do have to iterate through the list, that is true, but the actual deletion itself will only take O of 1 time.
Okay.
Yeah. I know that's a little confusing, like separating the idea of insertion from the idea of transversing through it, but the actual deletion itself will only take that amount of time. It won't take over 1. Okay. So let's do this. Uh-oh. So the first thing we are going to want to implement is this idea, this item, and then the address of the next item. This is called a node. And all a node is, it is storing the item and the address of the next item. And if it's a doubly linked list, it's storing the address of the previous item too. Okay, so let's go back. I'm sorry, there has to be a better way to do that. I just don't know what it is. Okay, so we are writing Python. So we're going to define our node first. What did I do? Any ideas as to what I should put in my init? So self.
Location.
Location. What do you mean by location?
I guess where the memory of where it's stored at.
Yeah. So where that current one is stored at?
Or the next.
The next one, yes. So next, definitely. So next. Anything else? Looking back at the idea of a node and what goes in it, what else needs to be there?
It's value.
It's value. Okay. And for now, we can just do. So for now, let's say in the case that we only have one node, self.next would be none. So we can put that there as the default, and self.data, self.value. Force of habit, sorry. Self.value equals value, and self.next equals next. So now what we can do, without even doing anything else, I should really save this file. Without doing anything else, I can write A is equal to a node, and that node contains the value 11. I can create another node, I can call it B. So these are just random nodes and random places in memory. And this contains 12. C contains 13. Now I can say A dot next equals B, B dot next equals C. Okay. Now, if I asked it to print A dot next, if I asked it to print A dot value, we should get back 11. Why did I not print A dot next?
There's a space after node B. That changes it or not, but
Rena, can you see what I did wrong?
It does printed phrase. It's printing as a node object, and then the memory reference at the end of it.
Right. I definitely don't want it to do that.
You might need to add your str gender method if you want to print like
Oh.
the value next.
Right. Okay. Oh, sorry. Can you guys see what I'm typing?
No, ma'am.
I can't see nothing.
Yeah, it looks like it's frozen.
That's not great. What about now?
Yep, that's good.
So what would I want to put in here? Any ideas?
In your string dunder method?
Print self dot. Yeah, I would think print self dot value. Yeah.
No.
Probably print itself and print whether next is none or not.
Okay, I'm not quite sure what's happening. We're gonna try something. I don't think we need a stir method actually. Let's just do this for now. I'm sorry guys, I don't know what to do.
What are you trying to print when you do a.next phrase?
Huh?
What are you trying to print? What do you want it to
This
display?
value.
You want the value of the next node, or
Yes, the value of the next node. So a.next is equal to b, and I want it to print b for me.
So
Oh, that's
print
dumb.
a.next
Data.
value.
Yes, that was not smart of me.
You mean dot value?
Yes. There we go. Okay. I was pretty sure we didn't need a stir method, and I was like, why do we need one? Okay. There we go. And I could, of course, keep on going like this if I really wanted to, but we don't need to. Any questions about that? Sorry that that was so loopy. Any questions about what happened there with this node and what it's doing?
That makes things a lot clearer.
Okay.
Yeah, I think I understand a linked list now.
Yay. Okay. Wonderful. So let's write another class, and let's call this class linked list. That was just a node. In this class, what we're trying to put in there is operations. So things like transversing through it, things like inserting, deleting. We're not going to do all of them because we need to move on. This is taking time. So let's say class linked list def.init. I don't want to do that. And this time we're going to include a head, a pointer to head. And all that is it's pointing to my very first node. So in our heads, when we think of a linked list, right, you're going first node, second node, third node, right? Well, in order for your computer to do that, it needs to be able to keep track of this is the first node, right? So that way it knows to move on to a second node, right? Because a pointer doesn't exist by itself for that first node, right? Does that make sense? So we need to create one for that first node, and we're going to call that first node head. So we're going to put that in here, and that's pretty much all we need to do for our init. To transverse through it, to traverse through it, there it is. What we're going to do is we're going to tell it that, what did I do? def traverse. We're going to tell it that our current node is equal to self dot head. Does it make sense why I did that?
Yes, ma'am.
So while current node is not none, I want it to print current node dot data for me. And once it's printed that, I want it to go ahead and move current node to current node dot next. Does that make sense? Right? So I'm
Yes.
changing my current node to the next node. And once it reaches none, it's just going to stop. So now let's go ahead and test that. So
Will it have to be current node dot value in this case instead of data?
you know what? I had a professor that insisted on data, and now it's stuck.
Is that like a Java
Oh no, we were not using Java.
accessor? No, yeah.
Yeah, she was just really picky. No idea why, but it's okay. So let's create our first linked list. Well, it's okay, except for the fact that I keep typing in data now. That's not quite okay. Linked list. So this first linked list is, we can just call it list one. Let's not complicate things. That's our first linked list. And we're gonna tell it, hey, list one, your head is equal to node 11. And then B can be equal to node 12, C 13. Okay. And now if I print, oh, I still have to add the next. I need to tell it what comes next. So head dot next equals B, and then B dot next equals C, and list. Now I'm gonna run my traverse method. I'm gonna clear that first. And it does it. Does everything that happened here make sense? Yeah, perfect.
I'm picking it up.
Any questions? That is great. So now we're going to move on. We're going to switch topics completely. We're going to talk about tuples and lists. They're very similar. They have very similar jobs. Does anybody know what those jobs are, what they do? You, of course, do not have to know what they do, but any ideas?
Yeah, you can change the items in a list or mutate it however you want, but a tuple, you cannot. It's kind of set.
Yeah. So a tuple is set. It's not mutable. Does that make sense to everybody? That idea of it doesn't change, a tuple can't change? Okay, cool. So let's run through this pretty quickly. Can somebody tell me the syntax for writing a list, at least in Python?
Brackets.
Brackets, exactly, 1, 2, and so forth. What about a tuple?
Parentheses.
Like
Yeah, curly brackets. I'm actually horrible at drawing those curly brackets. I've never succeeded, not once, at doing it.
I think for tuples, they might be just parentheses in Python.
That's what I thought. I thought a dictionary was curly brackets.
I'm so sorry.
Yeah, I think curly brackets using that way would create a set object.
Definitely would. I'm so sorry. Okay. And as Rena mentioned, the mutability is different. And he already told us this one can be changed. It is mutable. And this one can't be changed. So knowing that, does anybody know any advantages of using a list or of using a tuple? Anyone that you know or can maybe think of is perfect. It's perfect.
Yeah, so a tuple would be great for like grid coordinates. If you have a target designated, you're not going to want to change that coordinate versus a list, you might just want to store a bunch of data, move it around however you want. And so it's more nimble.
Yes, absolutely. So one big advantage of a tuple is the fact that it can't be changed. So when you don't want information to be changed, a tuple definitely makes sense. Any other advantages you can think of? Thank you for that, by the way.
I would assume because a tuple can't be changed, it might be a bit quicker to work with.
Yes, absolutely. So the way a list is implemented, it will hold on to extra space sometimes. So a tuple will also be slightly, it'll use less memory for sure. And it'll also be faster, slightly faster. Maybe not like, it might not matter to us like creating a tuple for like counting 1, 2, 3. It might not matter for us in those cases, but for very specific use cases, you might run into a situation where you're working and using a tuple definitely does matter because it's faster and uses less memory. Can we think of any advantages of using a list?
More versatile with
Yes.
being
Yeah. Any areas where you might want to use a list as opposed to using a tuple? Any ideas?
Yeah, if you don't know like the size that you really need for something.
Yes. I'm sorry, my handwriting is insane. My third grade teacher warned me. I just don't listen, but it's okay.
That's okay. Mine's even worse.
That's
Alrighty.
why we're all in the computer field and not writers.
This looks like a signature on a credit card machine.
Another example, another advantage of a tuple is that, so internally, we're going to talk about hash tables in a second, but internally, I actually don't know if we have time. Ankur, how are we on time? Is he still here?
Oh, it's totally up to you guys. I mean, definitely take breaks if you're going to go over an hour, but it's up to the students how long they want to stay in. Students are free to stay or leave, but definitely valuable information. So take your time.
So internally, sets, do we know what a set is in Python?
Yeah, isn't it just like a unique values? So you're not gonna have any repeating numbers or values,
Yeah.
I guess.
Yeah, absolutely. So another big difference is that whereas a tuple, like how we mentioned earlier, that a tuple, we can use it to store like locations because order matters in the tuple, right? So latitude and longitude for sure, it's going to stay that way in a tuple. And a set, order doesn't matter quite as much. So you wouldn't want, it doesn't like, it's unordered. But so my point was that in Python internally, sets and dictionaries are implemented through something called a hash table. And hash tables, simply put, are structures that map a key to a value, right? And that makes sense if you think about a dictionary and what it does, right? Are we confused on hash?
I mean, just a little. So what's the difference between a dictionary and a hash table if it's just keys and values?
That is the way I explained it is a vast oversimplification. A hash table it has other things. So it uses something also called hash functions to determine how to map them in the order in which it's going to let you see them. So a hash table can also implement a linked list inside of it. And I'm sorry, I'm making that so much more complicated. But for now, can we trust me that it's different?
Yes, ma'am.
We will get to it, I promise, just for now. What was I saying? Okay, so since lists are mutable, they can't be hashed. You can't map a key to a value with a list. However, a tuple, because you can't change it, can be hashed. I can map a key. I can use a tuple as a value. It can be hashed. That's complicated. It may not make sense right now, but hopefully it'll make sense in a second when we talk about hash tables. Okay. And I think we're good to move on. Okay. Now that I'm thinking about it, actually, do we have any questions first? Okay.
I'm sure they'll come.
Okay. Now that I'm thinking about it, we're going to skip through the hash table stuff for just a little bit, just because I think the stuff that Rena has to present is a little more valuable to you. Hash tables just sound complicated, but honestly, you will probably never be asked to implement one ever, because dictionaries and stuff like that are already implemented for you. So we're going to skip through it for now. And if we have time at the end, we will come back to them.
Yeah, Praise, do you mind if I share my screen? I think hash tables and graph and dictionaries are very similar. I think one thing that I would say though, and I don't know if this is the case for all programming languages, but I think the types in dictionaries are more specific, whereas in hash tables, I believe you can switch up the types. I would have to double check that, but that's one thing to note. Let me share my screen. Okay. So my part is relatively short. I just wanted to talk a little bit about graphs and trees. Can everybody see my screen right now?
Yes, ma'am.
Yep.
Okay, so graphs are super fun. They're a little bit more complex than linked lists, stacks, and queues, since they are not linear data structures, but they're essentially a collection of vertices and edges. I have like a very rough implementation here to give you a general idea of what goes on under the hood. So we have a class vertex which contains data and we'll know which edges are connected to it. And we have a class edge that contains data and also knows which node it starts and ends with. And then your class graph will just hold a collection of all of the vertices and all of the edges. Typically, it'll also have several other capabilities like adding and removing edges or vertices, checking if an edge or vertex is contained within the graph, get outgoing edges from a particular vertex, etc. And we have two main types of graphs. We have directed and undirected. So graphs can be used to represent all sorts of things. Most often, you'll probably see it used to represent a map. Does anybody have an idea of whether we would want to use a directed or undirected graph to represent a map? So the distinction between directed and undirected, sorry, I should have said this first, is that with an undirected graph, if A is connected to B, as we see here, then it's implied that B is also connected to A, which isn't the case for a directed graph. So directed graphs are direction specific. So if A is connected to B, B is not necessarily also connected to A.
So with that definition, I would think a map would be an undirected graph.
What if we have one-way roads?
Well, that road's still connected to the thing it came from.
It's just socially unacceptable to go the wrong way. You might hurt somebody, hurt people.
Yeah, so directed graphs are probably what you would want to use to represent like Google Maps or something. It can also be used to represent, like the nodes can be airports and the arrows can be flights from one airport to another airport, stuff like that. An undirected graph, one example I can think of is like a social media network. So like Facebook, where each node represents a user and the edge represents whether or not those two users are friends or connected with each other. So things where direction doesn't really matter. Yeah, let's talk about a specific type of graph, which is a tree. So a tree is just a root node that has children. We can recursively define this as a root node where each child of the tree is also a tree. So each subtree is the tree. And then this would be a directed graph since, for example, 7 is a child of 2, but 2 is not a child of 7. And then just in terms of terminology, we call the very top of the tree a root and nodes with no children leaves. So trees are super useful in different search algorithms. So we talked a little bit about binary search trees earlier. In terms of application, I have never used this outside of my data structures and algos class, but I know that it's used in various sorting algorithms where you can build a tree from a list. And then if you just do an in order traversal, that will yield you the sorted list. Yeah, but this is super useful because search is super quick. Does anybody know the big O?
The O of log n, probably.
Yes. Do we have any questions so far? Okay, great, we can move on. The last thing I wanted to touch a little bit about was stacks and queues. I know some people were wondering like what sort of applications we could do with this. And I just pulled up one example. In Python, you would just use a list as a stack or a queue since it has the same functionalities. In other languages like Java, you would probably want to use the queue from the Java library. But these are useful when you never need to index into the middle of the list and when you want to be able to have an element returned and removed simultaneously. So on the right side here, I have a BFS algorithm, a breadth-first search algorithm that I pulled from Geeks for Geeks, which uses a queue and essentially goes through a graph. And then on this line here where it says S equals Q, Q dot pop 0, pop will return and also remove that element from the list, traverses it top down, super efficient. Yeah, that's all I have. Does anybody have any questions? Okay, I can hand it back over to Praise.
Now, sorry, one question though. But for the
Yep.
queue, all done with so you're basically making use of a linked list, but just sticking to the functionality of append and pop because that's the only functionality that a queue would have.
Yeah.
Okay. But if you were to make a class that was a queue from scratch, you would basically make the class with yeah, as a linked list, but then only give it the functions of pop dependent. Right. Like I'm just trying to, would you look at queue as a different data structure or a subset of linked list, I guess?
So queues, linked lists, and stacks, I think are all like subcategories of lists. I don't know if I would think of queues in terms of a linked list. But you definitely could implement a queue using a linked list. So say we have a list with only the functionalities of append and delete. Those are pretty much the only two functionalities you would need to implement all three of the other list data structures.
Okay, thank you.
Yeah. Okay. Let me stop sharing my screen.
Okay, so real quick, let's talk about those hash tables. Okay, so let's say you work at a grocery store, and this grocery store, the owner is kind of a butt. He wishes it was still the 1950s, and he refuses. You see one of these machines here where people are checking out? He refuses. He said no. Instead, what he has is a book, and in said book, you have a list of all the items in the grocery store and all the prices. Now, remember I said he's a butt? He also refused to put them in order. He just like wrote them in as he got the item. So this list is unordered, and every time a customer comes up with something, you just have to like figure it out. See how unhappy they look? This is why they don't look happy, because it's going to take you a while. Okay, so let's say actually, how long would that take you? Let's say I wanted to go through each item in the list every single time a customer brought something up. What would be the runtime of that?
Oh, then.
Exactly. That's not great, especially when you have a long list of customers. Does anybody know what that search is called, where I go through every single
A linear search?
A linear search, yes. So now let's say I went ahead and I've been working here for a while and I'm tired of customers being mad at me. And I went ahead and I put all the items in an array, and I like put a tuple in there, and I was like, this item costs $99. This is an apple. It costs $300. Pies cost 3 million. And then I went ahead and I put them in order. Now I could run, so pretend this is ordered. Now I could run a binary search on it. You guys talked about that earlier. Does anybody remember what the runtime of that would be?
That would
Is
just
it
be on one.
nlog O of nlog n?
Yes. Log n. So it's definitely faster than this, but it still isn't quite fast enough for my angry customers. I try it out, it works better, the line is moving, but customers are still angry at me. I'm still getting yelled at. Now let's say I have a friend and her name is Buddy, and Buddy has worked at this grocery store for 900 years. So she has it all memorized. So Buddy's terrifying. Okay. So she has the entire book memorized. So I can just ask her, hey, Buddy, how much does the apples cost? And she can tell me how much it costs right away. So I can say Buddy's runtime is 01. Let's say now I wanted to create my own Buddy. I wanted to code out my own Buddy. Hash tables are going to help me do that. Now, before we jump into a hash table, let's talk about what a hash function is. So simply put, a hash function is taking a string and it's mapping it to numbers. That's what a hash function is doing for me. So let's say I put in apple, and this is my hash function machine. Every time let's say I get out 4, I put in pie, I'm going to get out, okay. It's supposed to look like this. Pretend it looks like the first one. Okay, I'm gonna get out 2, and so forth and so on. And every time I put in apple, every single time I put in apple into my little hash function here, I'm going to get out 4. Every single time I put in pie, I'm gonna get out 2, consistently like that. So this hash function would break if, let's say, I put in petunia and I got out 4, because each string, each like item is supposed to map to a different number, right? Now, why is that important?
So isn't a hash table just like an object or a dictionary then?
Yes, except we'll get into why it gets a little more. I've told you a little lie here, like a small one that I will clear up in a second. So why is that important? Why is it important that every single time that I map that out, I get the same number out? So remember, Apple gave out 4. So 0, 1, 2, 3, 4. Well, gave out 4. Well, apples cost 99 cents. Does that make sense? So pies gave me 3. Well, pies cost $3 million here. Does it make sense what it's doing for me?
So is that kind of like mapping a location to the value?
Yeah, it could be put that way, yes. $500 for my milk. And so forth and so on. And eventually my array is going to be full of prices and blah, 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 blah. So now when I ask, hey, what's the price of an apple? Rather than looking through my whole thing, I know apples at 4, apples are 99 cents. Does that make sense?
Yes, ma'am. So like the way I'm kind of like thinking about it is like it's a dictionary full of dictionaries.
Yeah, keep it that way. So the hash function is going to tell me exactly where my prices are stored, right? It's not going to tell me my price, it's just going to tell me where it's stored. And this way I don't have to search through it, and I achieve that wonderful O of 1 that I was looking for. So remember, it needs to be consistently mapped to the same index, right? Every single time I put an apple, I need to get at 4. And remember that different strings need to map to different places and so forth and so on. Okay, one thing that I didn't mention, I'm sorry, I'm looking at my notes. One thing that I didn't mention is that hash functions know how big my array is. So it's never gonna so if my array, it has a size of 9, it's never gonna like pop out, hey, put it in 11. It's not gonna do that. So just like this, we've built ourselves a buddy. These are probably the most complicated data structures you'll learn. These are, at least for me, it was the most complicated. And you will probably never have to implement it, like I said. There are also other names for them. So you'll hear them called dictionaries. You might hear them called hash maps. A bunch of other things you'll hear them called. But the advantage of them is that it is instant. It's very fast. I can get whatever I'm looking for instantly. So we're not going to implement it. It's okay.
How long does it take to build it?
You can build a very, very simple one in less than a minute or 2. Like
the hardest part, I would say, is probably making the hash function. There's one way to make it that involves like prime numbers, like mapping each key to some prime number and then adding something and then modding it by the size of your hash table, which yields like the most like spread apart value indexes so that you run into as few collisions as possible. But yeah, just to reiterate, your hash function is what maps your key to an index value. And then in that index value, it holds the value, which is like the key value pair. So I wouldn't actually necessarily think of it as a nested dictionary. I think it would probably be closer to just like a dictionary on its own. Praise, were you going to talk about collisions?
Yeah, actually, thank you. That's like the perfect segue. So about that lie I told you, remember how I told you they always map to different indexes? That was kind of a lie. It does not always do that. Because if you manage to write an amazing hash function that always does it, then congratulations. but more than likely you're going to end up with a collision. So imagine this is our array, and this is my hash function. And what we wanted to do ideally is when I put in apple, I wanted to send it to this one. I put in pie, I want pie to go to a different one. Milk, I want milk to go to a different one. But honestly, it is very, very difficult to write a hash function that does this. At least I didn't learn a simple way to do it. Rena, did you learn a good way to completely avoid collisions?
If you avoid collision, you're
I don't
actually
think there is a
hashtag
way.
bigger than your data item.
What, Don? I'm sorry to hear that.
If you use an algorithm to avoid collision, your hashtag ends up being bigger than your data item.
I'm not processing. I'm so sorry.
It's not necessary.
Okay, gotcha. So let's say I used a simple hash function. Let's say in this hash function, I was like, hey, map my stuff alphabetically. So I want you to put the A, like, I want you to put apple in 1, I want you to put banana in location 2, and so forth and so on. So at first, it's going to work out well for me. It's going to work out. So apple gets to go there. My apple brings out 1, and that's 99 cents. Pie is bringing out 3. That was, oh, sorry. That was, it's bringing out 0, sorry. 0, 1, 2, 3. That was 3 million. But let's say all of a sudden, I decide to get fancy, get on trend, and I'm like, I want avocados. Well, because of the hash function that I wrote, it's going to put it here in 0. This is a problem because what's already there?
Be the apples price.
Apples price. So now I have an issue. Is this apples? Is this avocados? I don't know if I spelled avocado correctly, and I'm not even going to try. I don't know. This is a collision. 2 keys have been assigned to the exact same slot. And it's obviously a problem because let's say my avocados are 9 million and you were only supposed to pay 99 cents for those apples. You're not going to be a happy customer. So what it's really going to do is create a linked list. Uh-oh, come back. Thank you. Create a linked list. So I'm going to end up with something like this, where I now have apples, and that maps to 99 cents. And then I have avocados, and that maps to 9 million, and so forth and so on. That's what it's going to do if I have a collision. Now, there are different ways to deal with the collision. This is the simplest one. This is probably the easiest one you can do. So now avocado and apples, they're mapped to the same slot, but there's a linked list of it. So let's say I want to know, I want to know the price of a pie. Well, that's still really easy to do. It's 3 million. But let's say I want to know the price of an avocado. That's a little slower than O of 1, right? Because now I've gotten here, I know it's a 0, but now I have to traverse through my linked list. Does that make sense?
So what determines the plate, like for the avocado, what determines the placement of that, and why would it collide, or why would it place in the same spot? Like what's determining the assigned value?
Absolutely. So it was the hash function that I gave it. I told it that I wanted to organize alphabetically. So I want A to be mapped to 0, B to be mapped to 1, so forth and so on, right? This is like a really easy hash function. This is like, your hash function doesn't have to be something fancy or elaborate. It could be as simple as this, but like all other hash functions, it's going to run into issues eventually where it's going to collide with something. Something is going to break. It's not really breaking, but it's going to collide with something else eventually. So mine collided very easily, very quickly, because I have two items with a A. And I told it, if it's A, I want you to pop out 0 for me. And the solution that I gave it to a collision was to create a linked list of those things.
Would that be the most efficient way of doing it? Is just doing a linked list at index 0?
I don't think so. Rena, can you think of, is there?
There are lots of ways to deal with collisions. Another way is linear probing, where essentially you check if the hash function yields you an index that's already taken. You just move to the next one and see if that one's free and then put your item there. The problem with this is that if you run into like a block of a bunch of indices that are already filled, then it's not super time efficient. But yeah, there are lots of ways to deal with collisions. I can definitely send some links in the chat.
Okay, so this is essentially a hash function / hash table. Again, you will likely never have to implement one of these outside of a data structures class, because most of them are already built into things like dictionaries and things of the sort. I think the last thing I want to talk about is we recognize that this linked list here has slowed down my hash table, right? Does that make sense that it's slowed it down?
Yes, ma'am.
Okay, well, that's it. And of course, if you want your hash table to work better, you should use a better hash function than what I just did here. It's not great. But yeah, do we have any questions?
When would you use a hash table, Grace, other than like in the real world and not for?
Well, you absolutely are. You're already using them. Whenever you have to use a dictionary, you're using one. A more specific example. Honestly, the best example I can give you is whenever, let's say I wanted to take grades, like write an application that takes in grades. This might be overkill for it, but a dictionary is like using a writing my own hash function would be overkill for that. But a dictionary is essentially this. So I hope that makes sense. Did that answer your question?
Yes.
Good. So that is all we have for you. But of course, we're happy to go talk about more. Any other questions?
For like a general data structure, so we've looked at like the main ones. Is there like a much larger list of data structures, like maybe like more efficient data structures or things like that, or are they all like subsets of basically what we've been talking about?
I think I'm trying to think of one that falls outside of what we've talked about. I can't right now. I don't know if Rena can think of anything that falls outside of everything we've talked about, covered. Yeah, they're like more, they're like you said, just they fall under these and they get more specific and have more specific use cases. Anything else?
So like implementing data structures on a class level, you might think about doing that if, like you're saying, for the specific use cases, you need it to be like faster than something else or for that specific case. So that's when you would probably like make the class and actually implement the data structure. Okay.
Yeah, yeah. I have friends who are implementing a very specific, like a very specific like I don't even know what to call it, substructure under graphs right now, because they're trying to map rivers in Africa. So depending on what your projects are, you might never use a tuple, but you might use a dictionary all the time. It just depends on what you are doing. All right, y'all. Well, thank you so much for coming. Hopefully we have not wasted your time. Thank you, y'all.
Thank you.
Thanks.
Thank you.
Yeah.
This
Thank
was a
you.
much needed lesson.
It was amazing. Thank you very much.
Also, we're happy to do more of these. So if you guys have any like requests on like particular topics or anything like that, we're more than happy to open more breakout rooms in the future.
Appreciate it.
All right.